Hello, let's talk about elastic collisions. So being an A-level student, you are expected to be able to calculate the outcome of elastic collision given the initial conditions. So let's use this one as an example. So for any collision, the total momentum must be conserved. So by PCOM, you can write out this line here. So this is the momentum of the 2 kilogram. This is the momentum of the 4 kilogram. -1 because it's a leftward velocity, and this is the momentum of the red ball after the collision. This is the momentum of the blue ball after the collision. So simplify this equation, you get equation 1. Now since we are told that this is an elastic collision, we know that the relative speed of approach is equal to the relative speed of separation. So 3 minus -1 is equal to V2 minus V1. So we call this equation 2. So now we are going to add equation 1 to equation 2 so that V1 and -V1 cancel each other out. So we are left with 5 equals to 3V2, which means V2 is 1.7 meter per second. And then we can sub this into equation 2, and then we get V1 to be -2.3 meter per second. So turns out after the collision, the blue ball will be going rightward at 1.7 meter per second, and the red ball will be moving leftward at 2.3 meter per second. So this is a very standard calculation. It always involves setting up two equations, one based on PCOM and one based on RSOA is equal to RSOS because it's an elastic collision. And then you are going to do the simultaneous equations thingy and arrive at the answers. Now I think it's actually more interesting to look at the graphs. So I've plotted on this graph here, momentum against time. So here we have the momentum of the two balls before the collisions, and here we have the momentum of the two balls after the collision. Of course, if you add up these two numbers, it's the same because momentum must be conserved, right? So what's the momentum of the two balls during the conditions itself? Well, actually, we don't know how this momentum changes to this momentum exactly, but let's assume that it changes linearly, alright? So if the red ball's momentum changes in this manner, then the blue balls must change exactly in this manner. They must be mirror images of each other, because whatever momentum lost by the red ball must be the momentum gained by the blue ball. It has to be so because the total momentum must remain constant, right? Even during the collision, the total momentum must be conserved. Okay, here I've also plotted the graph of velocity against time. So these are the velocities before the collision, these are the velocities after the collision. Now from this graph alone, you are able to tell that it's an elastic collision. How come? The gap between these two lines is actually the relative speed of approach, right? And the gap between these two lines is the relative speed of separation. So these two gaps are the same size. That means it's an elastic collision. So the red ball's velocity, how does it change from here to here? Let's assume that it changes linearly in a straight line, and the blue for the blue ball also a blue line. So from this graph alone, you should be able to tell which is the heavier ball. Remember, during a collision, the two balls experience an action-reaction pair, so they experience the same magnitude of force. So the heavier ball with a larger inertia will have a smaller acceleration. So you can tell that this must belong to the heavier ball and this must belong to the lighter ball. Okay, one more thing I want to highlight to you. So remember just now I told you that the total momentum of the two balls must be conserved all the time, even during collision. So what about the total kinetic energy? So if this is a total KE before the collision, then after the collision it must have the same total KE because it's an elastic collision. An elastic collision conserves the KE. But what about during the collision? Actually, from the momentum graph, you can tell that both balls are actually slowing down near the middle of the collision. So actually the total KE right at the middle of the collision definitely cannot be equals to the total KE before and after the collision. So this is a bit different from total momentum. Total momentum is conserved all the time. As for total KE, even for elastic collision, the total Ke is constant only before and after the collision. During the collision itself, the Ke actually dips. That means during the collision, the Ke is converted into some other kind of energy, maybe stored in the potential energy of the atoms in the two balls. However, as the two balls separate, the stored energy is converted back into Ke. 100% of all the Ke is converted back. And that's why it's an elastic collision. Alright, that's all. Ta-ta!